The time had arrived. The time is now. We're going to speak about NP. So first, an introduction. Okay, so P is the class of all decision problems that can be solved efficiently. Intuitively, this is all the problems that we are interested in because we can solve them efficiently with algorithms. NP is a set of all decision problems for which, if the answer is yes, we can verify the answer in polynomial time using a non-deterministic algorithm. What is a non-deterministic algorithm? Non-deterministic algorithm is an algorithm that is allowed to make choices. Now, we're not speaking here about a random choice. It's more along the line that it can get to a point in the algorithm where it has to make a decision, and it can call an oracle. And the oracle can tell it, go left, go right, jump, start dancing, etc. Now, the class NP is less natural than P, right? P is, of course, maybe the most natural class, but NP would be, once you get used to it, it's a very natural class. It's essentially, the way to think about those two classes is NP is about verifying, right? There is, one thing is to do something, and the other thing is to verify something. And verifying is much easier than building something, right? So you have to compute an independent set in a graph. That's hard. But if on the other hand, I give you an independent set in a graph, I give you vertices in the graph that I claim are independent set, you can verify it's an independent set. That's easy, right? So that's the difference between answering a question and verifying an answer, right? Usually verifying an answer, correctness of an answer, is much easier than coming up with an answer. So NP is this class. Again, the formal definition is a bit less intuitive, but we will go there. All the problem in NP would be solvable in exponential time. It usually would be like obvious. Usually the algorithm for those problems is just brute force enumeration. You enumerate all possible solutions and you check which one of them is correct and you're done. And of course, importantly, P would be contained in NP. So the ability, if I give you this access to the oracle, I make your algorithms significantly stronger. They can solve more problems. So P will be contained in NP. And of course, some of the problems in NP are in P, right? Because P is a subclass, so that's obvious. And the biggest question that theoretical computer science and to a larger extent all of computer science has faced beginning in the 70s, so at least 45 to 50 years, whether P is equal to NP. Namely, we have this large family of problems that are in NP, and we don't know if they're in P. We don't have an efficient algorithm to them. The belief, in fact, is that there is no efficient algorithm for them. But as far as we're concerned, it might be that P is equal to NP. That's extremely unlikely, but it might be, and that's the biggest question that is currently open in computer science. Solve this question and you would be famous. Okay, so here's a list of problems that we had seen that are all polynomially equivalent, although we only see the first three are equivalent and the last two equivalent. In fact, the two groups are equivalent, as we will see later on. We have no polynomial time algorithm for them. They are all in NP. And of course, there are much harder problems that are undecidable and so on, but we are speaking about problems that can be solved. And the question is, can any of those problems be solved efficiently? And what is common to all those problems? Well, the common thing for independent set, if vertex cover, set cover, vertex, I guess we already said that, SAT and tree-SAT. In fact, I don't think we talked explicitly about set cover, but we should. So all those problems, we did, right? Because vertex cover is essentially set cover. So, okay. So, or it is the generalization of vertex cover. So all those problems, the equivalent thing about them, that they are, if the answer is yes, I give you an instance of this problem and ask you, is there if the answer is yes, you can give me a short proof. By short, I mean polynomial in the size of the input, and I can verify that the answer is correct. And we will go through examples for that. So let's go through a quick example. If you give me a SAT formula, and I ask you, is there a satisfying assignment? If the answer is yes, you can just give me the assignment as a proof that yes, it's indeed, the answer is indeed yes, I'm not lying to you. And of course, taking the assignment and verifying that it's indeed satisfies the formula is easy, right? You just compute the formula. Independent set. The question is there an independent set in graph of size k? Well, you just need to give me the set of, if the answer is yes, you just need to give me the independent set, and I just check that it's independent. No pair of vertices are connected by an edge. Okay, and the last example is homework. And what do I mean by that? I mean by that if the homework questions, some of them might be hard or difficult or both. But hopefully, once I give you a solution, you can read it and make sure that it's correct. And if it's well written, you can do it quickly, right? You just read it and you think, oh, yes, that's the solution, that's correct, right? So checking things like homework things is easy. But this, I must say that this is for intuition. This is, of course, not formally correct, right? It's more along the intuition that solving a homework problem is hard, but if I give you a solution, verifying that it's correct, if you're careful enough, is easy. And there are, any natural problem almost that you can think of has this property. Sudoku is a good example. Sudoku, solving it takes some effort, but if I give you a solution, you just verify the properties of Sudoku and they hold. And Sudoku is one of those problems where if you generalize the problem to n by n grids, which people did, of course, then one can prove that they are NP complete. Namely, if you can solve them efficiently, then you can solve all problems in NP efficiently.